Dear friends, today we will discuss the mineral sampling and sample properties. Sampling theory and practice play an important role in mining and metallurgy. The objective of sampling in mineral processing is to estimate grades and contents of sampling units in an unbiased manner and with an acceptable and affordable degree of precision. Sampling units are classified as dynamic and static stochastic systems. Generally, sampling is the process of selecting a part of a whole such that a measured value for the part is an unbiased estimate for the whole. In mineral processing, a whole is referred to as a sampling unit such as mass of mill feed, dewatered concentrate or bullion, or a volume of cyclone overflow or tailings slurry. A sampling unit is classified as a dynamic stochastic system when sampled during transfer and as a static stochastic system when sampled while stationary. The validity of this method depends critically on how slurry flows in mineral processing plants are interrogated and how the variances of stochastic variables are estimated. Applied statistics provides scores of powerful techniques to test for bias, to estimate precision, to optimize sampling protocols, and to determine the degree of associative dependence between measured values in ordered sets. An overview: sampling is the selection and analysis of samples from various parts of mineral bodies in order to determine their composition and quality. Sampling is essential for evaluating a deposit, calculating its reserves, and selecting the method of extraction and the plan for working the minerals. Mineral sample preparation is a vital stage in the process of mineral analytical testing. The purpose of sample preparation is generally the production of homogeneous subsample representative of the material submitted to the laboratory. Correct preparation is critical to obtaining meaningful analytical results. The selection of the specific sample preparation procedures will depend on the type and size of the sample, the mineralogy, as well as the client's analytical and budgetary requirements. Mineral sample preparation includes geological sample preparation, sampling, drying of geological samples, crushing of geological samples, splitting of geological samples, pulverizing of geological samples, screening of geological material, core cutting, compositing, particle size analysis of geological samples, quarantine services for geological samples, sample storage and management for mineral clients. Mineral inspection and surveying sampling methods. There are 4 types of sampling methods, that is chemical, mineralogical, technical and technological. Chemical sampling is used to determine the amount of useful components and harmful impurities in deposits of metallic and many non-metallic minerals. Mineralogical sampling establishes the various grades of useful minerals. Technical sampling is used in analyzing minerals whose value depends on such mechanical and physical properties as strength, resistance to compression, wear under friction, flexibility, resistance to fire, resistance to aggressive chemical substances and electrical conductivity, etc. Technological sampling is used in testing a mineral's concentration, capacity for melting, or used in unprocessed form. Regardless of the type of sampling used, the process is divided into 3 stages, that is selecting, processing and analyzing the samples. First is the sample selection. Samples are selected in mining excavations by cutting a groove, scratching the surface, taking places or lumps, collecting residues from boreholes, or removing part of rock broken off during the sinking of mining shafts. Samples in mines are selected systematically so that evaluation of the quality of the mineral in the entire deposit or sections of the deposit can be made with the smallest number of samples taken from points that are a definite distance from one another. Samples from boreholes opening up deposits of solid minerals are selected by removing specimens from the bottom of or walls of the hole using special devices or by flushing out a drill part of the deposit with a flushing fluid. Second is sample processing. The most complex type of sample processing is the chemical sampling of the solid minerals. The sample, usually weighing several kilograms, is broken down by crushing, mixing and reduction to chemical samples weighing a few grams. The minimum weight of a chemical sample in the successive stages of the processing is monitored according to Zekort's formula, that is Q equals to Kd square, where Q is the weight of the sample in kilograms, D is the diameter of the largest particles of the crust sample in millimeters, and K is the coefficient of proportionality, which ranges from 0.05 to 0.83. Analyzing the sample in chemical sampling, existing chemical methods are used to analyze samples to determine the content of the valuable elements and harmful impurities. Next is the technical analysis. Technical analysis reveals mechanical and other physical properties, and technological analysis determines the most efficient ways of working, processing and using the minerals. For some types of mineral products, chemical sampling methods have been developed that can be used at the faces of mines and boreholes without taking samples, and this method uses the properties of the mineral and chemical composition of minerals that can be subjected to quantitative evaluation by special instruments at the site of the mineral raw material. The larger the sample, the more accurate sample results, as it represents the larger volume of material that has not been analyzed. The more sample one take and the closer they are together, the more accurately the average result will represent the larger volume of material that has not been analyzed. Next is to achieve an accurate result in sampling. It is vital that one should thoroughly clean all of the values from sampling equipment in between samples. As mineral deposits can be found at different stratas within a stream bed, a good sampling program does not only test in different geographical locations but also at the different layers within a stream bed. This is because it can often be more commercially productive to mine a deposit only down to a specified strata. Next is to be effective recovery equipment used in sampling must have the capability of concentrating the values which exist within the deposit. Where a special recovery equipment is needed and the sampling must be accomplished with portable dredging equipment, it is sometimes necessary to dredge the samples into floating catch container. Then the samples can be carefully processed on land. Care must be taken to ensure that foreign material is not introduced into the material being sampled, which can render the results inaccurate. Just as this has to do with the foreign materials from other geographical locations, it also has to do with materials from different strata within the stream bed if layers are being tested independently of each other. Then the smaller this sample being analyzed, the more results can be thrown off by the introduction of foreign material called as the contamination. Generally, tailings from a sampling recovery system should be carefully analyzed to see what values are being lost and whether steps can be taken to recover the values in a production operation. Ultimately, only the values that can be recovered during production should be included in the final business projections. A care must be given to measure the amount of raw volume that is excavated to extract a sample, because the values recovered must be related back to the amount of material that was removed and or processed to obtain the result. This relation will need to be measured against the volumes and cost associated with a potential production operation. Methods of sampling prospect openings such as trenches, test pits, shafts, tunnels and drifts are the same as for sampling development headings in operating mines. Suffice it is to say that different types of deposits require different sampling methods, in which number 1 is pitting. In areas where the ground is wet or labor is expensive, pits are best dug with a mechanical excavator. Pits dug to depths of 3 to 4 meters are common, and with large equipment, excavation to 6 meters can be achieved. In wet soft ground, any pit deeper than 1 meter is dangerous and boarding must be used. Diggers excavate rapidly and pits 3 to 4 meters deep can be dug, logged samples and refilled within an hour. In tropical regions, thick lateritic soil forms ideal conditions for pitting, and provided the soil is dry, vertical pits to 30-meter depth can be safely excavated. Now coming to trenching. Trenching is usually completed at right angles to the general strike to test and sample over long lengths as across a mineralized zone. Excavation can be either by hand, mechanical digger or by bulldozer on sloping ground. Excavated depths of up to 4 meters are common. Next is augering. Augering is the use of drill-like tools to take small samples or columns of subsurface deposits. These are also known as cores or boreholes. The advantage of hand augering is that it is fairly quick and easy to carry out in comparison to more extensive excavation. It can be used to test the depth of deposits or to retrieve material for further analysis. One auger hole may answer specific questions such as how deep is this ditch and what type of deposit is at the bottom. But when carried out over an area at regular intervals, an auger survey may give a very useful preview of the types and depths of deposits which may be encountered in subsequent information. These observations can be used to create a three-dimensional computer model of subsurface layers. The disadvantage of augering is that it gives almost no contextual information about the samples retrieved. For example, an auger may penetrate at a gravel cut or the flow deposit of a prehistoric roundhouse, but a slight smear of different colored soil may be all that would be visible in the auger sample. Number 4 is core sampling. Core sampling is technique used in underground or undersea exploration and prospecting. A core sample is a roughly cylindrical piece of subsurface material removed by a special drill and brought to the surface for examination. Such a sample is needed to ascertain bulk properties of underground rock such as its porosity and permeability, or to investigate the peculiar features of a given zone of strata, for example, to compare strata at a given level with those known to bear oil or gas. Number 5 is bulk sampling. Bulk sampling is the removing of large mineralized rock, typically over 50 tons, selected to be representative of the potential ore body in order to do mineral processing tests. Often the bulk sample will be a composite of material from development drifts and raises. Ideally, drift, round or other portions should be selected from geological mapping and prior sampling, handled separately, and should be stored temporarily on a pad for sampling if not directly processed. The bulk sample will consist of these components and will take into account the geological continuities. The appropriateness of the bulk sample will be related to its source, to the variability of the deposit, to the deposit morphology, and to anticipated problems. Sixth is the chip sampling. Chip sampling is another special drilling option under the custom drilling services domain. Rotary drilling rigs designed to use large volumes of the compressed air retrieve consolidated rock samples from varying depths. The resulting geological data allows for the quick assessment of the quality and quantity of the mineable reserves. Seventh is the channel sampling. This technique is generally used when sampling underground opening, that is drifts, tunnels, adits, crosscuts and trenches dug in rock. The best approach is to chip a sample of rock that is 1/2 to 1 inch deep and 6 inches wide for the full length of the wall being sampled. The rock that is chipped off this wall should be collected as it is removed and stored in sample bags, which represents a regular sample interval if the rock type is homogeneous. If there are changes in the rock type, then the sample interval should correspond to the changing rock types. If the rock is too hard to obtain a full width sample, it may be advisable to make a narrower sinusoidal channel from which to take the sample. Taking channel samples is a tedious process, but the samples are very good representatives of the rock of interest, and care must be exercised to ensure that the samples are correctly taken. Eighth is the grid sampling. Grid sampling can be particularly useful where there is a little prior knowledge of within field variability. It also avoids sampling bias that could result from the collection of an unrepresentative composite samples due to high portion of the subsamples collected from the same region. Two common types of the grid sampling include grid cell and grid point. Grid cell soil sampling randomly collects either one or multiple subsamples throughout the cell for a composite sample. A grid point soil sampling collects one or multiple subsamples around a georeferenced point within a grid or at a grid intersection. Ninth is the selective sampling. In this technique, the performance of the classifiers is improved by adding supplementary information to a training set. In general, there is a small set of labeled data and large set of unlabeled data. In addition, there exists a possibility of asking an expert or oracle for labeling additional data. Many methods of selective sampling have already been considered in two or multi-class problems. They select objects which are close to the description boundaries, for example, close to a margin or inside a margin of the support vector classifier, which have the most evenly split labels over a variation of the classifiers trained on multiple permutations of the labeled data or differing by the settings trained in and on independent sets of the features. 10th is the composite sampling. When samples are collected at frequent intervals at a station, analysis of each individual samples would be prohibitive in cost and for many streams would result in needless duplication. Consequently, the compositing of several samples into single samples for chemical analysis is a common practice, but it should be avoided whenever possible. Such composites are generally made on the basis of dissolved mineral content as indicated by measurements of conductivity of the daily samples supplemented by other easily obtained information such as concentration of chloride, river stage, weather conditions, appearance of samples and previous history of the stream. 11th is regions per sampling. Regions per sampling is done for mineral prospecting where samples are taken along the crest of ridges and spurs in an area that is being analyzed for minerals. It helps to define the footprint of the mineralized area. Minerals are naturally occurring inorganic uniform materials that have definite chemical and physical properties. To be classified as a true mineral, a substance must be a solid and have a crystal structure. It must also be inorganic, naturally occurring homogeneous substance with a defined chemical composition. Geologists identify minerals based on their physical and chemical properties. A description of these properties is listed below in this module. Many of these properties are controlled by the elements present in the mineral and their arrangement. The following are some of the physical and chemical properties of minerals that can be used to identify mineral for the purpose of sampling. Some of them are pure physical property or pure chemical property, while some of them can be considered as both physical and chemical property for the purpose of identification and sampling of minerals. Number 1 is the color, next is the streak, number 3 is hardness, next property is cleavage. Some examples are mica cleavage in one direction, feldspar it have cleavage in two directions, calcite, galena and halite cleavage in three directions. Next property is striations. Next is the crystalline structure. Some minerals form crystals if there is time and room for the crystals to form. The crystal pattern of a mineral is controlled by the internal arrangement of the atoms that make up the mineral. Seventh is the transparency or diaphanity. Diaphanity is a mineral's degree of transparency or ability to allow light to pass through it. The degree of transparency may also depend on the thickness of the mineral. Eighth property is tenacity. Tenacity is the characteristic that describes how the particles of a mineral hold together or resist separation. Tenacity is how tough a mineral is, how easily a mineral will break, split, crumble or change shape. Ninth property is magnetism. Magnetism is the characteristic that allows a mineral to attract or repel other magnetic materials. It can be difficult to determine the differences between the various types of magnetism, but it is worth knowing that there are distinctions made. If there is a magnetic attraction between minerals and a metal object, then the mineral has high iron content. Tenth property is luster. Luster is the property of mineral that indicates how much the surface of a mineral reflects light. The luster of a mineral is affected by the brilliance of light used to observe the mineral surface. 11th property is odor. Most minerals have no odor unless they are acted upon in one of the following ways, that is moistened, heated, breathed upon or rubbed. Next is the taste. Only soluble minerals have a taste, but it is very important that minerals not be placed in the mouth or on the tongue. Water soluble minerals, that is halides, sulfates, borates, may have a distinctive taste. A common example of minerals with distinct taste are halite, that is salty, and sylvite, that is bitter. Then next property is the feel. Soft minerals such as graphite, talc, serpentine and molybdenite often have a greasy feel to them. Next is specific gravity. A specific gravity of a mineral is a comparison or ratio of the weight of the mineral to the weight of an equal amount of water. The specific gravity of most minerals varies between 2.5 to 3 and is dependent upon both the atomic weight of its constituent atoms and how closely packed they are. In hand sample, one can quickly determine if a sample is low, moderate or high density. It is of particular use for unusually dense minerals such as barite, that is barium sulfate, and cerussite, that is PbCO3. Next is the acid test. This test is performed by dropping weak hydrochloric acid on the mineral. If it reacts, that is fizzes, then the mineral is calcite. This test will also help to identify the rocks, limestone and marble, because calcite is the principal mineral in both. Mineral exhibits effervescence if it reacts to weak acid by generating bubbles of gas. Dolomite will react when powdered or if the acid is heated. Other carbonate minerals such as siderite will effervesce slightly with strong or hot acids. Next property is twinning. Crystal twinning occurs when two separate crystals share some of the same crystal lattice points in a symmetrical manner. The result is an intergrowth of two separate crystals in a variety of specific configurations. The type of twinning can be a diagnostic tool in mineral identification. In this chapter, we studied the mineral sampling process, techniques of sampling and sample properties. The following conclusions can be drawn from this chapter. sampling procedures cover the particles of selecting representative quantities of test material in the field to evaluate bulk materials. Examples of the test materials are bulk, granular, solid, slurries, sludge, grains, and solid fuels. It is necessary to be able to sample bulk materials during shipment and during processing operations. The sample should be representative. It is important before collecting a sample to decide what the purpose of sample would be and then plan the sampling procedures accordingly so that it will be sufficiently representative for your purposes. Thank you very much.